Hello, and welcome. I'm glad you're here. Maybe you've had a long day, and your body is ready to sink into rest. Or maybe your mind craves something endless to wander through, like a quiet trail beneath the stars. Whatever brought you tonight, this is your space to let go. No rush, no pressure. Just the slow drift of thought, carried on calm tides of curiosity. You don't need to solve anything now. Just let your shoulders loosen, your breath fall into rhythm, steady and easy. Tonight, we'll explore one of the most irresistible questions of all. Does space ever end? Scientists have stared into the dark for centuries, and still the horizon whispers mystery, the edge of the observable universe, the fabric of space-time stretching, the possibility of infinity, or of hidden boundaries we cannot yet see. Each idea is both humbling and comforting, a reminder of how small we are and how vast the story around us truly is. So, as you rest, we'll travel together through 100 wonders, some proven, some imagined, each circling the same question, not to find the edge, but to feel its mystery. When we ask what it means for space to end, the question hides more layers than it seems. In everyday life, an end is clear: a wall, a shoreline, a door that will not open further. But when we stretch that idea into the cosmos, it begins to dissolve. Is an end the point where matter thins away into nothing? Is it the last place light can reach us? Or is it something stranger, the horizon beyond which even imagination struggles? Astronomers often begin with what they can measure, and that is the observable universe. This is the bubble of space wrapped around us, defined not by walls but by time. Light moves at a finite speed, and the universe has a finite age. That means we can only see so far, not because there is nothing beyond, but because the light from farther regions has not yet had enough time to arrive. That boundary lies about 46 billion light-years away in every direction, forming a sphere of vision. Yet this is not the end of space itself. It is simply the limit of what we can see, like fog on a morning road. Beyond the mist, the road may continue endlessly, but from where we stand, it disappears into silence. This distinction between the observable and the actual universe is one of the most important subtleties in cosmology. If the observable universe is like a room lit by a single lamp, the actual universe may be an entire mansion whose other rooms remain in darkness. We cannot peer into them, but their existence is no less possible. And because the cosmos is expanding, those unlit regions may be rushing farther away so quickly that no light from them will ever reach us, no matter how long we wait. The visible horizon is always changing, but some distances remain forever out of reach. So when people ask if space ends, one answer is that it does not end in the way a street ends in a cul-de-sac. Instead, it ends in horizons. These horizons are not material walls, but limits written into the fabric of time and geometry. There is the particle horizon, the farthest we can ever see because of the universe's age. There is the event horizon, the line beyond which galaxies recede so fast, carried by expansion, that no signal can ever return. Each is an edge, but not the kind we can touch. They are edges of knowledge, not of existence. The language itself tempts us toward misunderstanding. We imagine edges as hard and final. Yet, the universe offers boundaries that are soft and elastic. You might picture them as the surface of an inflating balloon. If you live on the balloon's skin, you can walk in any direction without finding a wall. Yet the surface has a finite area. From within that curved world, end is meaningless, even though there is a shape enclosing you. Some cosmologists think our universe may be like that, finite yet unbounded, curving back on itself in dimensions we cannot directly sense. Even if the universe is infinite, our access to it is not. The observable limit makes our cosmic vision feel like standing on the shore of an endless ocean at night. We see the waves lapping at our feet. We hear the breakers close to shore, but the deep horizon merges with the sky, leaving us to imagine what lies beyond. Infinity is possible, but so is finitude hidden in topologies too vast for comprehension. The truth is concealed not by secrecy, but by scale. This is why the idea of space ending is so slippery. It can mean the edge of what light has brought us. It can mean the edge of what will ever be possible to know. It can mean a literal physical boundary, though evidence suggests otherwise. Or it can mean no edge at all, just an infinite stretch that carries on past the reach of thought. Each meaning is valid in its own frame, but none exhausts the mystery. In the end, asking, "Does space end?" reveals more about us than about the cosmos. It shows our instinct to draw lines, to crave borders, to fit even infinity into a box. But the universe resists such neatness. Its boundaries are horizons, not walls. Its endings are perspectives, not final stops. To live within it is to dwell not at the center of a closed system, but at the edge of a vastness that always recedes as we approach. And perhaps that is the quiet gift of the question. It does not resolve into certainty, but it does open a space in our minds as boundless as the one outside our windows. A space where end becomes not a wall, but a doorway into wonder. As you drift further into rest, you can carry that thought with you, that the universe, whatever its shape or size, always gives you more to imagine than to conclude. When we talk about the observable universe, we are not describing the whole of existence, but the portion carved out by light and time. Imagine turning on a lantern in a vast, fog-covered plain. The glow only reaches so far, and what lies beyond the fog remains hidden. Our cosmic lantern is the age of the universe itself, and the fog is the speed of light. Light, though astonishingly swift, is not infinite. It takes time to travel, and because the universe has only been unfolding for about 13.8 billion years, we can only receive signals that have had enough time to cross that gulf. Yet expansion complicates the picture. While the universe is 13.8 billion years old, the farthest galaxies we can observe are not 13.8 billion light-years away. They are about 46 billion light-years distant, because as light journeyed toward us, space itself stretched, pulling the galaxies farther apart, even as their ancient beams inched forward. This sphere, stretching 46 billion light-years in every direction, forms the observable universe. It is a bubble centered on us, not because Earth holds a special place, but because every observer, no matter where they stand, finds themselves at the center of their own bubble. Just as every raindrop reflects the world around it in its own circle of light, every point in the cosmos has its own horizon defined by the reach of signals. The observable universe is therefore not an objective boundary, but a deeply personal one, tied to location and time. Wherever you are, the limit of what you can see stretches out evenly, a cosmic horizon that drifts with you. But this horizon is not a wall. It does not mark the edge of existence, nor does it tell us the universe ends there. Beyond that shimmering boundary, the cosmos may continue without limit. We cannot know for certain what lies past it, but the prevailing understanding is that the universe extends far, perhaps infinitely, beyond our sight. It is like standing at the shore of a dark ocean. The water does not end where your eyes can no longer trace the horizon. The sea simply stretches farther than your senses allow. The observable universe, then, is not the whole story, but only the portion we can witness, the stage, lit by light's patient travel across eons. Consider what it means that light itself is the messenger. When we gaze into the night sky, we are not seeing stars as they are, but as they were. A star, 1,000 light-years away, is shown to us 1,000 years in the past. The faint glow of distant galaxies may carry the history of 10 billion years. In this sense, the observable universe is not just a map of space, but of time. The farther we look, the further back we travel, until the view becomes so ancient that it approaches the very beginning. At the furthest edge of visibility lies the cosmic microwave background, a faint afterglow of the Big Bang itself, light released when the universe was only 380,000 years old. It forms the most distant screen upon which photons can paint an image. Beyond that, light could not travel freely. It was trapped in a fog of plasma, scattering endlessly until the universe cooled enough to become transparent. That ancient fog is the final curtain for our eyes, though not necessarily the end of all things. This creates a paradox of scale. The observable universe is enormous, almost unimaginably so, yet it is also incomplete. We live within a bubble that stretches farther than human travel can ever hope to reach, yet we are aware, humbly, that this bubble is not the cosmos itself. In fact, what we can see might be only a sliver of what exists. If the universe is infinite, then the observable region is like a single page torn from an endless book. If it is finite but unbounded, the horizon hides the full curvature of the whole, the way a traveler walking across Earth might never realize at first that the planet curves beneath their feet. It is natural to ask what lies outside this sphere of sight. Do galaxies continue on, repeating the familiar shapes we see close by? Do entirely different cosmic landscapes unfold, with structures so unlike ours that we would struggle to name them? Or are there boundaries we cannot yet conceive, where the physics we know bends into something stranger? We may never know for certain, because the observable limit is not a veil we can lift. It is a horizon written into the laws of light itself, and as far as physics tells us, no message from beyond can ever arrive. Yet this limit is not a failure but a kind of beauty. The observable universe gives us a glimpse, an extraordinary one, into both the vastness of space and the depth of time. Within it we have discovered billions of galaxies, each one cradling billions of stars. We have traced cosmic webs stretching across unimaginable scales, knots and filaments of matter, weaving patterns that resemble neurons or rivers branching. We have reached back nearly to the dawn of creation, catching whispers of the universe in its infancy. To hold all that within one horizon is already miraculous. That there may be more beyond, perhaps infinitely more, is not discouraging but humbling. Think of it this way. The observable universe is a circle of candlelight on a vast dark plane. The circle is wide, flickering, immense, and beyond it, the plane stretches further into shadow. We cannot see it, but we know it is there, waiting beyond our reach. The fact that the light has not yet arrived is not a flaw in the cosmos, but a reminder of how young we are as witnesses. We are still standing near the lamp's first glow, looking outward into a night that has no end. So when we say the observable universe, we are not drawing the universe's boundary. We are tracing the outline of our vision. It is a line not between something and nothing, but between the known and the unseen. It reminds us that space is bigger than sight, bigger than time, bigger than even our capacity to imagine. The horizon does not diminish the cosmos. It deepens it, giving us the quiet thrill of knowing that behind everything we see, there is always more waiting in silence. In the early 20th century, when telescopes were beginning to peer deeper into the cosmos than ever before, most scientists assumed that the universe was static. Stars burned, galaxies shone, and the night sky appeared eternal and unchanging on the grandest scale. Then came a discovery that shifted everything, the realization that space itself was expanding. The man most closely linked to this revelation was Edwin Hubble, who in the 1,920 seconds noticed something strange in the light coming from distant galaxies. Their light was stretched, shifted toward the red end of the spectrum. The farther away the galaxy, the greater the shift. At first glance, it might have seemed that the galaxies were moving through space at tremendous speeds, but the deeper truth was stranger still. It was not the galaxies fleeing like birds startled from a tree. It was the fabric of space itself that was swelling, carrying the galaxies with it like leaves on a rising tide. This was not merely motion but a reimagining of motion. To describe it, scientists often reach for metaphors that bring the unimaginable closer to home. One of the most enduring is the raisin bread analogy. Imagine dough rising in an oven, speckled with raisins. As the dough expands, each raisin finds every other raisin drifting farther away, not because they are crawling through the dough, but because the dough itself is stretching. If you lived on a raisin and looked out at your neighbors, you would see them all receding, and the more distant they were, the faster they would appear to move away. In the universe, galaxies play the role of raisins, and the dough is the very fabric of space-time. No single raisin sits at the center, and no raisin is privileged. The expansion looks the same from every vantage point, just as every galaxy perceives itself surrounded by others rushing away. What makes this expansion so remarkable is that it does not require the galaxies to propel themselves. A galaxy billions of light-years away is not accelerating with rocket engines, nor is it straining against friction or drag. It is simply being carried. Space is not a stage upon which galaxies move. It is the fabric being stretched, and the galaxies are bound to it. This difference matters because it explains why galaxies can appear to separate faster than the speed of light without violating Einstein's cosmic speed limit. Nothing is breaking the rule, because nothing is racing through space at that impossible pace. Instead, it is space itself that is swelling, enlarging the distance between objects in a way that the laws of relativity allow. The realization of expansion changed how we imagine the universe's history. If space is stretching now, then in the past it must have been smaller, denser, hotter. Trace the process backward far enough, and all the galaxies, stars, and atoms converge into a primordial moment we call the Big Bang. It was not an explosion flinging matter outward into a void, as fireworks scatter sparks into night. It was the beginning of space itself, the birth of the very stage upon which everything now unfolds. This subtlety is easy to lose, because our minds are wired to picture things flying outward from a central point. But the Big Bang happened everywhere at once, because everywhere was only then being created. Expansion also reshaped our sense of what distance means. If the universe were static, distance would be simple, like counting steps across a meadow. But in an expanding cosmos, distance is dynamic. Light, leaving a distant galaxy billions of years ago, has had to travel through a fabric that has been stretching all the while. So by the time the light arrives, the source galaxy is far more distant than it was when the journey began. This is why the observable universe extends out 46 billion light-years, even though the universe itself is only 13.8 billion years old. The stage has been swelling beneath the footprints of the photons, dragging the finish line farther away as the race was being run. There is something both unsettling and soothing about this picture. Unsettling, because it means the universe has no fixed frame, no solid ground on which to anchor our imagination. Galaxies do not merely drift through emptiness, but are embedded in a restless fabric that will not stay still. Soothing, because it reveals that our place in the cosmos is not marginal but universal. No matter where you stand, you see the same grand pattern of galaxies receding, the same gentle arithmetic of stretching. The universe does not single out a special location for its center, because the center is everywhere. And yet, expansion is not uniform in its effects. Gravity tugs against it, knitting stars into galaxies and galaxies into clusters. Within these bound knots, the cosmic stretch is powerless. Our Milky Way will not be torn apart by expansion. Its stars are too tightly bound. But on the grander scales, beyond the pull of clusters, expansion reigns. It stretches the voids between galactic superclusters, pushing the islands of matter farther apart across the dark ocean of space. In billions of years, the night sky itself will change, with distant galaxies receding beyond the horizon, their light stretched too far into darkness to ever reach us again. The stars we see today may become lonely beacons in an ever emptier sky, reminders of a time when the universe was brighter and closer knit. The expanding universe is not just a scientific model, but a profound shift in perspective. It tells us that change is written into the cosmos itself, that growth and separation are not accidents, but inevitabilities. It hints at futures where galaxies vanish beyond sight, where the fabric stretches so relentlessly that matter itself may be pulled thin, or where expansion slows and reverses, folding everything back into a final embrace. Each possibility is contained in the same truth, that the universe is dynamic, never frozen, always unfolding. And so we return to Hubble, standing at his telescope nearly a century ago, tracing faint smudges of light and finding in them the fingerprints of expansion. His observations cracked open the heavens, revealing that the cosmos is not a static cathedral, but a living, breathing expanse. What he glimpsed was not just galaxies, but the movement of the stage itself, a universe swelling like bread in an oven, raisins parting from raisins, stars sliding silently apart. That gentle stretching, too vast to feel and too patient to notice, continues even now, reshaping the night above your head this very moment. When we gaze at the night sky, every twinkle of starlight carries with it a subtle message. It is not only brightness and color we see, but also the imprint of motion, distance, and time. Astronomers learned long ago that light, like sound, can shift depending on the motion of its source. When an ambulance races toward you, its siren rises in pitch. As it speeds away, the sound falls. This is the Doppler effect, the stretching and squeezing of waves depending on relative movement. Light, though faster and finer, obeys the same law. If a star or galaxy moves toward us, its light shifts toward the blue end of the spectrum, compressed to shorter wavelengths. If it moves away, the waves are stretched, sliding into red. This red shift is the cosmic fingerprint of recession, the signature that galaxies are not static beacons, but are retreating with the expansion of space itself. At first, this might seem a minor technical detail, but it is the very key to how we measure the universe. Light is not just a glow, it is information encoded across billions of years of travel. Each photon is like a messenger carrying a stamped letter from the past, its envelope slightly stretched by the journey. By carefully reading those stamps, the precise way light is reddened, we can measure how fast the source is moving away, and thus how far it lies across the void. It is an astonishing thought. We do not travel to galaxies to know their distances. Instead, we let their ancient light, warped and tinted by expansion, come to us. The practical magic of this method lies in spectral lines, those thin, sharp markers of chemical elements. Every atom leaves behind a pattern of absorption or emission lines, as distinct as a fingerprint. Hydrogen, oxygen, carbon, each sings its own spectral song. When we observe a galaxy, we can compare the position of its lines to those measured in the laboratory. If they are shifted toward the red, we know the light has been stretched, and by exactly how much. This gives us not just velocity but distance, because the expansion of space links the two. The farther a galaxy is, the faster it recedes, and the greater its redshift. This relation, first mapped by Hubble, became the foundation of modern cosmology, transforming a patch of sky into a chart of cosmic history. Imagine, then, that every beam of light is like a rubber band stretched across time. A photon might begin its journey when the universe was young, vibrating in a crisp blue. As billions of years pass, the space through which it travels lengthens, and the photon's wavelength is pulled with it. By the time it reaches us, the once blue light may have become red, softened not by fatigue, but by the patient stretching of space-time. The universe is not static scenery, but an elastic loom, weaving light into longer threads as it ages. This stretching is more than a curiosity. It reveals the scale of time itself. Some of the faintest galaxies we observe today are so redshifted that their light has taken over 13 billion years to reach us. When we look at them, we see them as they were when stars had only just begun to form, when galaxies were tiny sparks compared to their modern grandeur. Redshift allows us to step back through epochs we could never otherwise touch, turning the telescope into a kind of time machine. In every direction, the deeper we look, the redder the light becomes, until eventually it fades into microwaves. The afterglow of the Big Bang. It is worth pausing to realize how counterintuitive this is. We are used to thinking of color as something immediate, like the shade of a rose or the blue of a summer sky. Yet in cosmology, color is history. A galaxy's redness is not merely its hue, but a chronicle of distance, velocity, and age. The universe writes its autobiography in shifting light, and all we must do is learn to read it. The simplicity is deceptive, because behind the gentle tint lies the story of space itself, swelling, bending, and reshaping every photon it touches. There is also a quiet poetry in how redshift stretches our sense of scale. Light that left a galaxy when Earth was not yet formed has been traveling ever since, passing by countless stars, slipping through vast voids, weaving its way across cosmic filaments. Along the way, the very corridor it traveled elongated, as if the universe wanted to ensure the journey would never be straightforward. By the time that light finally brushes against our eyes or sensors, it carries not only the image of a galaxy, but also the memory of the universe's restless expansion. And still, redshift is not absolute certainty, but part of a larger puzzle. It tells us how far light has traveled and how space has grown, but it also hints at the invisible forces at work. The discovery that distant galaxies were more redshifted than expected revealed dark energy, the mysterious pressure accelerating expansion. Thus, a simple shift in color opened the door to one of the greatest enigmas in physics. From the faint whisper of stretched light, we deduce the presence of an unseen force that shapes the destiny of the cosmos. To measure redshift, then, is to measure not just distance, but destiny. Each spectral line is a marker, a tally of the universe's growth. Together, they compose a chart of expansion, a map that tells us we are living in a cosmos that began hot and dense, then stretched into the vast coolness of today, and will continue stretching into futures we can only imagine. Without redshift, the universe would be a static painting. With it, the cosmos becomes a moving story, each chapter written in waves of light sliding slowly toward the red. So the next time you see the night sky glowing faintly, remember that every star and galaxy is whispering across time, its message encoded in stretched light. To us, it may appear as beauty, but to those who listen closely, it is also knowledge. It is the language of expansion, the measure of distance, the proof that the universe is not still but endlessly unfolding. Light does not arrive unchanged. It arrives bearing the imprint of the cosmos itself, stretched and softened, as though the universe has pressed its fingerprint into every photon before passing it on. When people first hear that galaxies can recede from us faster than the speed of light, it sounds like science breaking its own rules. Einstein's theory of relativity tells us nothing can move through space faster than light, and yet cosmology insists that distant galaxies are slipping away at superluminal speeds. The paradox dissolves when we realize that it is not the galaxies themselves racing through the cosmos. It is the fabric of space itself that is stretching, carrying them with it. The law remains intact. No object can locally travel faster than light, but relativity places no speed limit on the expansion of space itself. Imagine painting dots on the surface of a balloon and then inflating it. The dots do not crawl across the surface. They remain still while the rubber between them stretches. From the perspective of one dot, the others recede, and the farther away they are, the faster they appear to flee. Scale this analogy to the universe, and you begin to glimpse the truth. Galaxies are not engines tearing across emptiness, but raisins embedded in rising dough. The dough is space-time, and as it swells, the raisins naturally drift apart. The further apart they start, the faster the gulf between them grows. Beyond a certain distance, The expansion can carry them away faster than light itself, not because they are sprinting through the cosmos, but because the cosmos is lengthening the road beneath them. This distinction is subtle but crucial. Relativity forbids signals or particles from outracing light within space, but when it comes to the growth of space itself, no such prohibition applies. The galaxies at the edge of our vision may appear to retreat faster than light, but this does not allow them to send us messages that cheat the cosmic speed limit. In fact, it means the opposite. Their light will never reach us, no matter how long we wait. They are receding, not just quickly, but irrevocably, carried beyond a horizon from which no signal can return. This is the cosmic event horizon, a boundary written not in walls of stone, but in the mathematics of space-time itself. The beauty of this lies in its counterintuitive nature. From our vantage, we can see galaxies nearly 14 billion years in the past. Their photons, emitted when the universe was young, have threaded their way through an expanding medium to arrive here. But those same galaxies, now far more distant, are rushing away at such tremendous speeds that the light they emit today will never cross the gulf. We see them not as they are, but as they were, and one day, even that ghostly image will fade as the expansion redshifts their light into oblivion. They are like ships drifting past the horizon of an ocean, their sails catching the last glint of sunset before vanishing forever into darkness. It is humbling to think that most of the universe lies in this unreachable realm. Already the majority of galaxies are beyond the limit of communication, carried away by the accelerating expansion driven by dark energy. Our cosmic neighborhood, the galaxies nearest to us, remain bound together by gravity, but the wider cosmos is slipping beyond our grasp. In time, only a handful of nearby galaxies will remain visible, while the rest recede into eternal night. Future astronomers, looking out, may find themselves in a lonely sky, never suspecting the universe was once so vast and filled with light. And yet, this does not diminish the grandeur of what we see today. It enhances it. For every photon arriving at our telescopes is a gift wrestled from the edges of possibility, a survivor of the stretching road. These photons have endured a journey across expanding space, their wavelengths pulled longer, their colors softened, their energy thinned. They are living proof of a universe not static but restless, swelling and reshaping itself even as we measure it. To say galaxies recede faster than light is not to claim chaos, but to acknowledge a deeper order, one that permits horizons and expansion without breaking the sacred limit of relativity. General relativity is the key to holding this paradox together. Einstein's equations describe not just matter and motion, but the curvature of space-time itself. They reveal a universe in which distances are not fixed but malleable, where geometry evolves and the metric that defines separation can change. Within this framework, faster than light ceases to be a simple notion of speed. It becomes a feature of geometry itself. A galaxy crossing an expanding distance is not violating physics any more than a dot on a balloon violates the rubber by riding its surface. The rules remain intact, even as our intuition struggles to catch up. It is tempting to wonder what it feels like, in those distant galaxies, to be carried away. Do their inhabitants, if they exist, see us fleeing faster than light as well? The answer is yes. From their point of view, we are the ones receding, slipping beyond their horizon. Every observer lives at the center of their own cosmic bubble. Every horizon is personal, and every galaxy sees the universe expanding away. There is no privileged vantage point, no cosmic anchor. Expansion is democratic, universal, written into the very structure of reality. So, when we say galaxies move faster than light, it is not a violation, but a revelation. It tells us that the universe is stranger and more supple than our everyday sense of speed and motion. It tells us that horizons exist not because the cosmos is small, but because it is too vast, too dynamic, too alive with change. And it reminds us that even as we measure and chart the heavens, there will always be realms beyond our touch, retreating forever, leaving only their fading echoes in the starlight that washes over our world. When you step outside on a clear night and look up, the stars seem to scatter across a flat dome of sky. Our senses whisper that space itself is simple, a stage stretched endlessly in every direction. But the true geometry of the universe is more subtle, and for decades, scientists have asked, what is the actual shape of everything? To answer, we must think in ways that stretch beyond everyday experience, because the shape of space is not about objects curving within it, but about space itself being curved. General relativity, Einstein's great insight, taught us that mass and energy bend space-time. On small scales, that curvature is what we feel as gravity. But on the grandest scale, when we ask about the universe as a whole, we must consider whether space itself bends into some vast form, flat like an infinite sheet, closed like the surface of a sphere, or open like a saddle that curves endlessly outward. Each possibility carries with it a different fate, a different destiny for the cosmos. If the universe is flat, then parallel lines remain parallel forever, and triangles obey the rules we learn in school. The angles add neatly to 180 degrees. This flatness implies an infinite stretch of space, unbounded, without edges, extending in every direction like an endless plane. It suggests that the cosmic density of matter and energy is precisely balanced, poised at the critical threshold where gravity pulls but never quite folds the universe back upon itself. To live in a flat universe is to live in a cosmos finely tuned, balanced on the razor's edge between collapse and unending expansion. But suppose the universe is closed, curved like the surface of a balloon. In this geometry, parallel lines that begin side by side may eventually converge, like the lines of longitude on Earth meeting at the poles. Triangles drawn on such a surface add up to more than 180 degrees, their angles swelling with the curvature. If our universe is closed, it is finite but unbounded, like the surface of the balloon. You could travel forever in one direction and eventually circle back to where you began, never encountering a wall, but always looping through the same cosmic terrain. This kind of universe might one day halt its expansion, pulled back by its own gravity into a final collapse, a big crunch mirroring the Big Bang. And then there is the open universe, shaped like a saddle. In this geometry, parallel lines diverge, forever parting as they extend. Triangles add up to less than 180 degrees. Space curves outward endlessly, stretching without limit, destined for eternal expansion. An open universe is infinite too, but it carries with it a sense of instability, a geometry that is never closed, never cyclical, forever unfolding into colder and lonelier futures. To imagine these shapes is to wrestle with metaphors. The balloon analogy works well for the closed cosmos. Paint dots on its surface, inflate it, and watch them drift apart without any center on the surface itself. The saddle represents openness, a fabric forever stretching outward, and for flatness, we picture an infinite sheet, uniform and unbending. Each image is only an approximation, of course, because the universe is not two-dimensional. Its curvature is not something we can step outside to see. Instead, we infer it by measuring the patterns of light itself, the way ancient photons have stretched and bent as they cross cosmic distances. The most telling clue comes from the cosmic microwave background, that faint afterglow of the Big Bang. Tiny ripples in this radiation, frozen patterns from the universe's infancy, spread across the sky like a cosmic fingerprint. By measuring the apparent size of those ripples, astronomers can deduce the geometry of space. If space were closed, the ripples would appear larger. If open, smaller. The astonishing result, gathered from satellites like WMAP and Planck, is that the universe is flat to within a tiny margin of error. Not perfectly flat, perhaps, but so close that it stretches beyond our comprehension. Whether it is truly infinite or merely unimaginably vast remains uncertain. But for all practical purposes, we live in a flat cosmos. Yet the mystery deepens, because flatness requires exquisite balance. The amount of matter and energy must be tuned so precisely that it seems almost miraculous. To explain this, cosmologists invoke inflation, a period in the earliest fractions of a second when the universe expanded faster than light, ironing out curvature and leaving behind a nearly flat cosmos. It is as if the wrinkles were smoothed from the fabric before it ever had a chance to fold. The result is the vast, nearly flat expanse we observe today. Still, our imagination lingers on the alternatives. To picture living in a closed universe, knowing that space loops back on itself, is to imagine an endless cosmic voyage with no edge but always a return. To dwell in an open universe is to feel the tilt of infinity, lines forever parting, structures drifting apart until even atoms might dissolve. To rest in a flat universe is to sit on the knife's edge of geometry, balanced between collapse and eternal expansion. A cosmos stretched taut like a perfect canvas. In truth, the shape of space is not just a mathematical curiosity, it is the architecture of existence itself. It defines what journeys are possible, what futures await, and what mysteries remain hidden beyond the horizon. Whether balloon, saddle, or sheet, the universe holds its shape in silence, revealing it only to those who listen closely to ancient light. And so we look up, our senses whispering of flat skies, while our equations tell us of geometries far stranger. The shape of space is not something we can touch, but it shapes us all the same, guiding the destinies of galaxies, stars, and every breath we take beneath the quiet dome of night. Long before there were stars, before galaxies spun their spirals of light, before even atoms could hold themselves together, the universe glowed with a dense, searing brilliance. In those first few 100,000 years after the Big Bang, everything was packed into a thick, hot plasma, where photons ricocheted endlessly off free electrons, unable to travel freely. The cosmos was not yet transparent. It was more like a fog, so bright that no eye could have endured it. And then, around 380,000 years after the beginning, the fog lifted. Electrons found partners in protons, forming the first stable atoms, and the photons, at last, slipped free. That release became the oldest light we can still see today, the cosmic microwave background. To look at this ancient glow is to see a baby picture of the universe. The galaxies and stars we know today did not yet exist. Instead, what we glimpse is a young cosmos, uniform yet trembling with tiny ripples, subtle variations in temperature and density that would, over billions of years, grow into everything we now recognize as structure. The microwave background is not dramatic to the naked eye. It would appear as a faint wash of microwaves invisible to our senses. But to sensitive instruments, it is a canvas of exquisite detail, mottled with patches just a few degrees hotter or colder than their neighbors. Those slight differences were the seeds of cosmic architecture, the first hints of the web of galaxies, clusters, and voids that now stretch across the heavens. It is humbling to realize that this light has traveled for nearly 14 billion years to reach us. Each photon in the microwave background has wandered across an expanding universe, stretched and softened by the growth of space itself. What was once searing radiation has cooled with time, its wavelength stretched until it now bathes us as a faint microwave signal. The entire universe is awash in it, a low, steady glow filling every corner of the sky. If you could tune an old television to static, a small fraction of the snow on the screen would come directly from this ancient light. The baby picture of the universe whispers even in forgotten living rooms. For astronomers, the cosmic microwave background is more than a relic. It is a wall, the furthest we can possibly see. Beyond it lies a universe that existed before transparency, a time when light could not travel freely. No telescope, no matter how powerful, can peer past that curtain, using ordinary photons, because there are no photons older than that moment. The microwave background forms a cosmic horizon, the surface of last scattering, beyond which the cosmos becomes opaque to light. It is the ultimate limit of vision, not because space ends there, but because light itself could not pass through the earlier fog. And yet, within that limit, the microwave background tells us a staggering amount. The patterns of its faint ripples reveal the geometry of space, the density of matter, the presence of mysterious dark matter, and even the fingerprints of dark energy. It is as though the young universe whispered its blueprint into the photons before releasing them, leaving us a message coded in temperature maps and polarization patterns. By listening closely to that message, cosmologists can reconstruct the entire story of cosmic evolution, from the smallest quantum fluctuations in the earliest instants to the great clusters of galaxies we see today. The discovery of this light came almost by accident. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were testing a sensitive antenna in New Jersey when they detected a persistent hiss of microwave noise. They cleaned the equipment, shooed away pigeons nesting in the horn, and still the signal remained. What they had stumbled upon was not interference, but the faint glow of the cosmos itself, whispering across all of space. Their discovery confirmed predictions made by theorists and gave powerful evidence that the Big Bang was not just an idea, but the true origin of the universe. Since then, satellites like COBE, WMAP, and Planck have mapped the microwave background with astonishing precision, turning static into a detailed portrait of the infant cosmos. When you see images of the cosmic microwave background, the colorful speckles are not stars or galaxies, but tiny fluctuations in temperature, measured to 1 part in 100,000. They look like noise, yet they are the seeds of all order, the starting points from which gravity sculpted the universe. From those slight variations arose the grand cosmic web, the filaments of galaxies spanning billions of light years, the clusters where stars ignite, the voids where darkness prevails. The microwave background is not just a picture of the past, it is the foundation of everything that followed. And still, it reminds us of limits. Beyond that wall, our sight cannot go. Whatever happened in the first split seconds of the universe, whether cosmic inflation stretched space in an instant, whether other realms of physics flickered into being, we must infer through indirect signs, because light itself cannot testify. The microwave background is both gift and barrier, the earliest whisper we can catch, and also the boundary beyond which silence falls. It is as though the universe has granted us one great photograph of its childhood and then turned its face away, leaving us to guess at its birth. Yet, perhaps that is enough. In that single image, in that faint bath of microwaves, we find both proof of beginnings and a map of what is to come. We find a cosmos that remembers its infancy, carrying its history forward in every photon. And when we tune our instruments to listen, we are not just scientists looking backward. We are children holding a photograph of our own earliest days, humbled by the knowledge that we, too, are part of the story that began in that glowing fog. The cosmic microwave background is quiet. It does not blaze or roar, but in its silence lies the most profound revelation of all. The universe remembers, and through that memory, across billions of years and billions of light years, it allows us, fleeting creatures on a small world, to remember with it. When we speak of infinity, we are really speaking of the limits of our own imagination. The mind can picture large numbers, stacks of zeros reaching higher than mountains. Yet infinity is not just a bigger number. It is something stranger, a concept without end, without boundary, a horizon that recedes no matter how far we walk toward it. In everyday life, nothing we touch is infinite. Everything we know comes with borders. Books have last pages, oceans have shores, lives have final breaths. To grasp the idea of an infinite universe is to push against the deepest habits of human thought. Science approaches the question carefully, not with sweeping claims but with measurements and models. When cosmologists ask whether space is infinite or finite, they are asking about its geometry and topology. A flat universe, balanced exactly at the critical density, could extend endlessly, its expanse without boundary. A curved, closed universe might be finite, looping back on itself the way the surface of a sphere does. An open universe, negatively curved like a saddle, could also stretch into infinity. Infinity in physics is not a vague gesture toward forever. It is a precise outcome of equations, a structure with rules, even if it is immeasurable in practice. The most unsettling part is that a universe can be finite and yet have no edge. This is the idea of being finite, but unbounded, a phrase that sounds like a riddle until you imagine the Earth. Our planet's surface is finite. You could measure its area, but there is no edge you could fall from. You could walk endlessly in one direction and never encounter a wall, only the looping return to where you began. In the same way, if the universe is closed, it may be finite, but without borders, a cosmos that curves back on itself so subtly that we cannot yet perceive the roundness. The boundary we instinctively expect may simply not exist. Philosophy lingers in this discussion as much as science does. The infinite has always been a canvas for wonder and unease. The Greeks debated whether infinity could exist in the physical world or only as an abstraction in mathematics. Medieval thinkers wrestled with the idea of a universe without limits, often treating infinity as a divine attribute, something beyond human or earthly reach. Today, even armed with equations and observations, we are still haunted by the same paradoxes. To imagine infinity is to strain at the edges of thought itself, and yet the measurements we have point toward a universe that is, to the best of our ability to tell, flat. And flatness, if exact, means infinity, a cosmos without end, stretching in all directions, bigger than any number can hold. If this is true, then every patch of space we can see is only the tiniest fragment of an endless expanse. Galaxies would continue forever, stars forming and dying in regions we will never glimpse, worlds turning around suns that will never share their light with us. Infinity is not only vast, it is unreachable. Still, infinity may not be the final word. Our instruments are limited, and what looks flat to us may, on larger scales, curve into closure. We may live in a universe so large that its curvature is beyond detection, making it appear infinite even if it loops back on itself in ways we cannot measure. The truth may be that our cosmic home is finite, but on a scale so great that to us it feels endless. In this sense, the question is not only scientific but existential. Do we live in a boundless ocean, or in a globe so vast that its edges are forever beyond our sight? Infinity, if it is real, also carries strange consequences. In an infinite universe, every possible arrangement of matter must eventually occur. Somewhere, unimaginably far away, there could be another Earth, another you, sitting beneath another night sky, wondering the same thoughts. This is not mysticism, but mathematics. Infinity contains repetition, the guarantee that all configurations repeat if space goes on without end. To some, this is exhilarating. To others, unsettling. To think of endless copies of ourselves scattered across eternity is to feel both insignificant and strangely eternal. Finite yet unbounded universes avoid these paradoxes but replace them with others. In such a cosmos, the journey outward might one day return you home, though the trip would be so long it defies practical imagining. The universe would be self-contained, a grand loop with no beyond. This kind of finitude has its own poetry. Everything is included, nothing lies outside, the cosmos, a complete and seamless whole. In the end, infinity versus finitude is not only a question of geometry, but a question of perspective. Our minds hunger for closure, for knowing whether space ends or continues forever. But perhaps the answer, whatever it may be, matters less than the act of asking. To stand beneath the night sky and wonder whether it continues forever is to recognize how small we are and how vast the canvas that holds us. The stars do not resolve the paradox for us, but they invite us into it, into the quiet awe of existing in a universe that may never be fully grasped. Infinity is not a place we can travel to. It is an idea, a horizon of thought, a mirror of the boundless mystery we inhabit, whether the universe is truly infinite or only so vast it feels that way. The effect on us is the same. We live within a cosmos too large to measure, too deep to hold, a space that stretches our imagination until it breaks and then continues beyond. When we ask where space might end, the question folds into layers because the universe does not give us just one horizon but many. Each horizon is a kind of limit, a boundary not of walls but of knowledge, written by the rules of light, gravity, and expansion. To explore them is to peel back veils, one after another, finding that each edge conceals yet another beyond it. The first is the particle horizon, the simplest to imagine. This is the farthest distance light has had time to travel since the birth of the universe. Because the cosmos is about 13.8 billion years old, we might expect this horizon to be about 13.8 billion light years away. But the expansion of space complicates the story. As light traveled, the fabric through which it moved was stretching, dragging the finish line ever farther. What we now call the particle horizon lies some 46 billion light years in every direction, forming the boundary of the observable universe. It is not a true edge of reality, but the edge of what has had time to reveal itself. Beyond it, the universe continues, silent to us for now, waiting on signals that may never arrive. Beyond the particle horizon, there is another limit, more subtle and more final, the event horizon. This horizon is not about what we can see today, but about what we can ever see. Because the expansion of the universe is accelerating under the influence of dark energy, there are galaxies whose light emitted now will never, in any future, reach us. They are receding faster than light itself. Not by their own motion, but because the space between us grows too quickly. The event horizon is the invisible line that separates the reachable from the unreachable. Galaxies already beyond it are like ships sailing into a fog, so swift and thick that no sound, no signal, no message can ever return. We may see them as they were long ago, their ancient photons still crossing the gulf, but we will never see them as they are today. In time, even those echoes will vanish into darkness. Then there is the Hubble horizon, sometimes called the Hubble radius. It is not an absolute wall but a useful marker, the distance at which galaxies recede at the speed of light, according to Hubble's law. Inside this sphere, light emitted now can, in principle, reach us, eventually. Beyond it, expansion carries galaxies away too swiftly. The Hubble horizon is more like a shifting shoreline, a mathematical threshold that helps us map cosmic motion, but it is not the final word. Light can sometimes cheat this border, slipping across as expansion rates change, giving us glimpses of galaxies that seem, paradoxically, too far to be seen. Horizons in cosmology are never as simple as fences. They move, bend, and redefine themselves as the universe evolves. What is striking about these horizons is how personal they are. Each observer, no matter where they are in the universe, finds themselves at the center of their own sphere of visibility. Every galaxy, every star, every planet has its own horizons, defined not by the cosmos itself, but by its perspective within it. The universe is democratic in this way. No vantage point is privileged. Your horizon is yours, and someone in a galaxy billions of light years away will have their own, overlapping but not identical. Reality is stitched together from countless such spheres, each a bubble of perception floating in an ocean without edges. Philosophically, horizons challenge our instinct for certainty. We are creatures who long to know what lies beyond the next hill, what waits past the horizon of the sea. But in cosmology, Horizons are not obstacles we can climb over. They are fundamental limits written into space-time itself. Beyond the event horizon, no amount of effort, no technology, no voyage of exploration can pierce the barrier. These are horizons we cannot cross, only imagine. And yet, there is comfort in knowing that horizons do not mean emptiness. Beyond the particle horizon, beyond the event horizon, the universe still exists, still evolves, still spins its galaxies and lights its stars. The fact that we cannot see them does not erase them. They are there, writing chapters of cosmic history we will never read, playing out dramas of light and gravity beyond the reach of our eyes. The universe is richer than our perception, greater than our horizons. So when we speak of the edge of space, it is not a single boundary but many. The particle horizon marks what we have seen. The event horizon marks what we will never see. The Hubble horizon marks what expands too quickly to hold. Each is a reminder that reality is layered, that knowledge has limits, and that wonder grows precisely from those limits. The sky above is not a window that shows us everything, but a veil that reveals only enough to remind us how much more lies beyond. In the end, horizons are not walls but invitations. They ask us to contemplate not just the known but the unknowable, to sit with the truth that some mysteries will remain forever beyond us. And perhaps that is why horizons feel both haunting and beautiful. They show us where our sight ends, and in doing so, they remind us that the universe itself never does. In the beginning, there was no space to expand into, no time to tick forward, no distance to measure. The Big Bang was not an explosion bursting inside a pre-existing void. It was the sudden birth of space itself, the unfolding of a stage where none had stood before. Everything, matter, energy, time, and geometry, was compressed into a state so dense and hot that ordinary language falters. Then, in the tiniest fraction of a second, something extraordinary happened. Inflation. The universe did not simply expand, it inflated, faster than light, an almost inconceivable swelling that transformed the cosmos from subatomic to astronomical in less than a heartbeat. During this moment, the scale of the universe doubled again and again, billions of times over, in less than a blink. Regions once close enough to touch were pulled so far apart that no signal could ever cross between them again. The seeds of everything we see today, galaxies, clusters, the great cosmic web, were stretched across unimaginable distances, frozen as faint ripples in the fabric of space-time. Inflation smoothed the universe, ironing away wrinkles, leaving behind the near uniformity we still detect in the cosmic microwave background. Without this sudden burst, the cosmos we know would not exist in such harmonious balance. And yet, the rules were not broken. Nothing outran light in the traditional sense. Galaxies were not tearing through space faster than photons could chase them. Instead, it was space itself expanding, carrying matter along as though it were painted on a balloon. The speed of light governs motion within space, but no law forbids space itself from stretching at any pace. Inflation exploited this freedom, expanding space-time at rates that defy intuition, leaving us to marvel at a loophole written into the very fabric of reality. One of the most haunting implications of inflation is that it may never have stopped everywhere. While our region of the cosmos slowed into a calmer expansion, other regions may still be inflating, budding off into new universes with their own laws and constants. This idea, called eternal inflation, paints a picture of a multiverse, countless universes, each sealed away from the others by the relentless swelling of space between them. We may live in one cosmic bubble among an endless froth of others, each isolated forever, like lanterns adrift on a dark sea, their lights never reaching one another. The multiverse is speculation, yes, but it arises naturally from the mathematics of inflation. Quantum fluctuations, tiny jitters of energy, are stretched during inflation into vast separations, creating regions where inflation ends and regions where it continues. The result is a patchwork of cosmic domains, some like ours, others perhaps governed by different physical laws. To think of this is to stretch imagination itself. Our entire observable universe, with its galaxies numbering in the trillions, may be nothing more than a single bubble in an eternal foam. Even if we never see those other bubbles, inflation leaves fingerprints we can detect. The slight irregularities in the microwave background are traces of quantum fluctuations magnified to cosmic scales. The uniformity of temperature across the sky, despite regions being too far apart to ever exchange signals, is explained by inflation stretching them from once neighboring points. Even the geometry of the universe, its remarkable flatness, is a relic of inflation's smoothing. Each of these observations whispers that the universe truly did inflate in that first sliver of time. There is a quiet poetry in knowing that everything we see began as infinitesimal ripples, amplified by inflation into the structure of reality itself. The galaxies that shine, the stars that burn, the planets that cradle life, all owe their existence to quantum jitters stretched beyond imagining. What feels solid and immense was seated in a moment smaller than the blink of an eye, when the universe was younger than the flicker of thought. And though we call it the Big Bang, the name hides more than it reveals. It was not a bang in space, but the making of space. It was not an eruption from somewhere, but the birth of everywhere. Inflation ensured that the cosmos would not be a chaotic spray of matter, but an ordered, expanding sea, vast enough to nurture galaxies and gentle enough to last for billions of years. It gave us the conditions not just for stars, but for the possibility of life, thought, and wonder. So when you look at the night sky, at the cold light of stars born billions of years ago, you are also looking back to that first instant when space swelled faster than light, when the universe leapt from the microscopic to the cosmic in a heartbeat. Inflation is the reason there is a sky to gaze upon at all. It is the reason there are horizons to ponder, galaxies to study, and mysteries to ask. And hidden in its mathematics is the tantalizing hint that beyond our horizon, beyond even our universe, lie realms we will never touch, born in the same great surge, each carrying its own version of forever. Inflation is both a scientific theory and a philosophical turning point. It teaches us that the cosmos is not just vast, but stranger than vastness alone can capture. It began not in chaos, but in a sudden, extraordinary order that still shapes us. And in its whispers of other universes, it reminds us that even our greatest questions may be only the beginning of a deeper mystery, one that swells just beyond the horizon, expanding endlessly into the unknown. When you imagine setting out across the universe, it feels natural to think of it as endless. Travel far enough, you might suppose, and you would only continue drifting outward, farther and farther, with no return. But space does not have to behave that way. It could be finite and still without an edge, shaped in such a way that a journey in one direction might eventually bring you back to your starting point. This is not just the stuff of fantasy. It is a real possibility rooted in the mathematics of topology, the study of shapes and surfaces stretched across dimensions too large for us to see. Consider the surface of the earth. To the creatures who first roamed it, the land seemed flat and boundless. Only much later did we understand it as a sphere, finite yet unbounded. There are no edges where the ground falls away into nothingness. Instead, if you walk steadily in one direction, you will eventually circle back to where you began. A spherical universe would work in much the same way, only with 3 dimensions of space instead of 2. There would be no wall, no final frontier, only a looping path that carries you home. Physicists sometimes describe this idea using analogies from video games. Imagine a game in which your character walks off the right side of the screen and instantly reappears on the left, or flies upward only to emerge again from the bottom. The world feels infinite, yet it is stitched together by hidden rules. Mathematicians call such spaces compact, meaning they are finite but without edges. A three-dimensional version of this could mean that if you traveled in a straight line for long enough, you might one day spot your own galaxy ahead of you. Not because you've leapt across space, but because space itself loops. Of course, the distances involved are staggering. If the universe does wrap around, the circumference could be so vast that no ship or signal could ever make the full circuit within the lifetime of stars. We would never complete the loop, but the principle remains. A cosmos with no boundary does not have to be infinite. It may be curved back on itself, a seamless whole in which every path is circular, even if the circle is too large to trace. Astronomers have looked for evidence of such topology in the sky. One possible sign would be repeated patterns in the cosmic microwave background, the faint glow of the Big Bang. If the universe loops, light could have circled around, arriving at us from multiple directions, leaving mirrored fingerprints across the heavens. So far, no such repeating signatures have been found. The universe appears, at least on scales we can measure, to be simply connected, stretching outward without detectable loops. Yet our tools are limited, and the absence of evidence is not proof of absence. It may be that the universe curves back on itself beyond our cosmic horizon in ways we cannot yet perceive. The philosophical implications are as intriguing as the scientific ones. An infinite universe suggests endless variety, galaxies and stars continuing forever, no two views of the night sky ever identical. A finite but unbounded universe suggests a closed totality, a cosmic whole in which all that exists is already included, a self-contained realm with no outside. Each vision changes how we think of our place. Infinity dwarfs us with immensity. Finitude enfolds us within a seamless entirety. Both are humbling. Both stretch imagination beyond its comfort. It is also possible that the truth is stranger still. The universe could have a topology more complex than a simple sphere or saddle. It could be shaped like a three-dimensional torus, the analog of a donut, with multiple looping directions. It could be twisted or folded in ways that mathematics permits, but the human mind struggles to picture. Topology frees space from the limits of ordinary geometry, allowing structures that are finite, edgeless, and deeply counterintuitive. If you pause to imagine traveling through such a cosmos, the feeling is both eerie and beautiful. You would never meet an end, never find a wall of stars beyond which lies nothing. Instead, the journey would be eternal, yet not into infinity, but into a loop where the familiar might one day return. Home is not only behind you, but also unimaginably far ahead, waiting in disguise. Perhaps the universe is infinite, flat and unending, an ocean without shores. Perhaps it is finite, a grand loop that circles upon itself. Or perhaps its topology is so strange that neither picture fits, a shape hidden beyond our horizons. Whatever the truth, the question itself reveals the richness of our mystery. To ask whether space loops back on itself is to step into the deep poetry of existence, where science and imagination intertwine. And if someday we discover that space truly does curve and close, that every path is a circle too vast to walk, then the universe will not be smaller for it. It will be grander still, a self-contained eternity in which every journey leads us not to an edge, but, eventually, back to where we began. The idea of the multiverse begins where our own universe leaves off, in the silence beyond the cosmic horizon. If inflation truly happened, and the evidence we see in the cosmic microwave background suggests it did, then it may not have been a one-time event. Inflation may continue eternally, blossoming new regions of space-time like soap bubbles foaming into existence. Each bubble would be its own universe, sealed away by the unstoppable swelling of the space between them. We live in one such bubble, our cosmos bounded by its own history of expansion, while beyond our reach, others expand, flicker, and evolve, each with its own fate. In this picture, our universe is not the whole but a fragment of something vaster, The multiverse is not a universe of galaxies, but a universe of universes, each bubble isolated, each carrying its own laws of physics. Some may look much like ours, with stars, galaxies, and perhaps life. Others may be alien beyond imagining, with dimensions folded strangely, forces unbalanced, or even no stable matter at all. Infinity, when applied to universes themselves, does not simply multiply what we know. It transforms it, opening the possibility that reality itself is more varied than any dream. Theories of higher dimensions add another layer to this vision. In string theory, the fundamental particles of our world are not points but tiny vibrating strings, their patterns determined by the shape of hidden dimensions curled up beyond our sight. In this view, our universe might be a three-dimensional membrane, a brain, floating in a higher dimensional space. Other brains may drift nearby, invisible to us, whole universes layered like sheets of paper in a greater dimensional stack. On rare occasions, such brains could collide, releasing energies vast enough to resemble new Big Bangs. Our own beginning might have been the echo of such a collision, a tremor in a higher dimensional landscape. The thought that space might harbor other universes alongside ours, separated not by distance, but by dimensional walls, stretches imagination into unfamiliar territory. If we could step into those higher dimensions, perhaps the divide would vanish, and we would see not a single universe, but a grander structure where countless universes coexist. Yet trapped within our brain, we perceive only our own, as if dwelling in one room of an endless mansion, never seeing the others beyond the walls. The philosophical consequences of this are staggering. If there are infinite universes, then every possible configuration of reality must occur somewhere. In one, the laws of physics are such that galaxies never form. In another, stars burn out swiftly, leaving no time for life. And in yet others, perhaps countless others, life flourishes, minds evolve, civilizations wander beneath different skies. Somewhere, in the infinite sprawl of possibility, there may be another you, and another, each making different choices, each living out variations of a story that can never meet your own. It is tempting to see this as science slipping into myth, but the seeds of the multiverse grow from equations, not imagination alone. Inflation's mathematics naturally leads to eternal branching. String theory, seeking consistency, requires extra dimensions, which invite whole landscapes of universes defined by how those dimensions fold. Quantum mechanics, too, with its many worlds interpretation, whispers of parallel realities where every quantum choice is played out in full. The multiverse is not one idea but many, converging from different directions, each pointing to a cosmos richer than we can see. And yet, the evidence is elusive. By definition, other universes lie beyond our horizon, cut off from observation. Still, some physicists search for indirect clues. Perhaps faint scars in the cosmic microwave background could betray a collision between our bubble and another. Perhaps gravitational waves could carry signatures of higher dimensional interactions. So far, the data is silent, the evidence just beyond our grasp. But silence is not proof of emptiness. It is simply another horizon, another limit of what we can yet know. The multiverse, whether real or not, changes how we think of ourselves. In a single solitary universe, our story is unique, fragile, unrepeatable. In an infinite multiverse, our story is one among endless variations, precious not for its rarity, but for the very fact of its existence amid infinite possibility. Both visions inspire awe, though in different keys. One offers singularity, the other abundance. Both remind us how narrow the band of our perception is, and how vast the mystery that stretches beyond it. To ask if the multiverse exists is to ask if our universe is all that there is, or merely one spark in a storm of creation. The answer may remain hidden forever, locked behind the walls of horizons we cannot cross. But the question itself reshapes our understanding. reminding us that even the most complete map of our cosmos may be only a fragment of a greater whole. And so, when you gaze into the night sky, know that you may not be looking into a single universe at all, but into one bubble among many, suspended in a sea of endless possibility. Perhaps somewhere, just beyond the horizon of our knowing, other skies blaze with other stars, other stories unfold, and other beings wonder, as we do, whether they too are alone. For most of human history, we imagined the universe as something stable. The stars seemed fixed in the heavens, the galaxies drifting at a measured pace, the cosmos a grand but predictable stage. Even after Hubble revealed expansion, it was easy to assume that gravity, slow and patient, would one day tug everything back together, or at the very least bring the expansion to a halt. But then came the discovery that overturned all expectation. The universe is not slowing down, it is speeding up. Some hidden force is pulling space apart faster and faster, stretching the fabric of the cosmos in a way nothing else can explain. We call it dark energy, though the name is less an answer than an admission of ignorance. The evidence came from distant supernovae, explosions so bright they can be seen across billions of light years. Astronomers use them as cosmic mile markers, their luminosity allowing precise measurements of distance. In the late 1992, two teams, working independently, found that these supernovae appeared dimmer than expected. The light was not just stretched by expansion. The galaxies were farther away than they should have been if the universe's expansion were steady or slowing. The only explanation was that expansion had accelerated, driven by something pushing outward with a repulsive force stronger than gravity's pull. What is remarkable is not just that space expands, but that the rate of expansion changes. In the early universe, matter and radiation dominated, their gravity working to slow growth. But as space itself grew, the density of matter thinned, while dark energy's influence remained constant, or perhaps even strengthened. Billions of years ago, gravity still had the upper hand. Then, a few billion years ago, dark energy overtook it. And since then, the expansion has been not just ongoing but accelerating, a runaway growth that grows more dramatic with time. What is this dark energy? The simplest explanation is the cosmological constant, a term Einstein himself once introduced into his equations of general relativity. It acts like an intrinsic energy of empty space, a vacuum energy that does not dilute as the universe expands. If this is true, then dark energy is woven into the very structure of reality, a property of space itself. But there are other possibilities. Perhaps dark energy changes over time. Perhaps it interacts with matter in subtle ways. Perhaps it reflects some deeper physics we have not yet glimpsed. At present, we cannot say. It is the dominant component of the universe, accounting for about 70% of all energy, and yet it remains a mystery as deep as any we have ever faced. The implications for the future of the cosmos are profound. If dark energy remains constant, the universe will continue to accelerate forever. Galaxies beyond our local group will slip from view, their light stretched into invisibility. The night sky will grow emptier, the great cosmic web thinning into isolation. Stars will burn out, galaxies will dim, and the cosmos will end not in fire, but in a slow, eternal fading, the big freeze. If dark energy strengthens with time, an even stranger fate awaits. Expansion could grow so violent that eventually galaxies, stars, planets, and even atoms themselves are torn apart, ripped by the relentless stretching of space-time. This scenario is known as the Big Rip, an ending in which not even matter survives. But if dark energy weakens or reverses, gravity might one day regain its hold. The expansion could slow, halt, and eventually reverse, collapsing into a big crunch that mirrors the Big Bang, perhaps seeding another cycle of cosmic birth. Each possibility flows from the behavior of a force we cannot yet name, a presence we only infer from the way it shapes the expansion of space. What makes dark energy so haunting is that it is both intimate and unreachable. It fills every corner of space, woven into the fabric around us, closer than our own breath. And yet it cannot be seen, touched, or harnessed. It is the quiet architect of the universe's fate, moving invisibly, deciding whether existence will fade into silence, collapse into fire, or tear itself apart. To study it is to face the edge of knowledge, where equations extend beyond comprehension and observations stretch into the unknown. And still, the discovery of dark energy is not despair but wonder. It reveals that the cosmos is not a static backdrop, but a dynamic, restless entity, evolving in ways more surprising than we could ever have predicted. It humbles us, reminding us that even after centuries of study, the universe still holds secrets that redefine everything we thought we knew. To live at a time when we have uncovered this mystery is to stand at the threshold of one of the greatest adventures in science. Dark energy is a name we give to our ignorance, but it is also a promise that the universe still has depths to explore, that the story of existence is not finished, that mystery is not a barrier, but an invitation. And while we cannot yet say how the cosmos will end, we can marvel at the fact that we are here, between beginning and ending, able to wonder at all. The universe, for all its grandeur, carries within it the quiet seed of its own ending. From the moment of the Big Bang, expansion has been its heartbeat, and gravity its counterweight. For billions of years, these forces have danced together, shaping galaxies, igniting stars, and weaving the cosmic web. Yet this balance cannot last forever. Just as stars exhaust their fuel and galaxies drift apart, the universe itself must face an ending. The question is not whether it ends, but how. Fire, ice, or silence. The possibilities are stark, and each one speaks to a different fate written into the laws of physics. One possibility is the Big Freeze, also called heat death. This is the slowest and perhaps the most haunting of endings. As expansion continues, galaxies move farther apart, their light stretched thinner and dimmer. Stars one by one burn through their fuel, leaving behind white dwarfs, neutron stars, and black holes. Over unimaginable stretches of time, even those remnants cool, fading into darkness. Black holes, once thought eternal, eventually evaporate through Hawking radiation, disappearing into whispers of energy. The universe approaches absolute zero, a state of maximum entropy, where all energy is evenly distributed and no process can occur. Nothing moves, nothing changes, nothing shines. The Big Freeze is not an ending of violence but of silence, a cosmic twilight stretching into eternity. Another scenario is the Big Rip, a fate born of dark energy's relentless grip. If this mysterious force grows stronger with time, expansion will not only accelerate, but accelerate without bound. Galaxies will be pulled away from one another faster than light, vanishing beyond each other's horizons. Then the gravity-binding galaxies themselves will fail, tearing them apart. Stars will be ripped from their orbits, planets torn from their suns. Eventually, the expansion will overwhelm even atoms, ripping apart the very fabric of matter. In this vision, the universe ends in violence. Not fire, exactly, but a shredding of everything into nothing. The Big Rip is an ending of dissolution, the very opposite of cohesion, where even the building blocks of existence are undone. There is also the Big Crunch, an ending that mirrors the beginning. If the density of matter were high enough, gravity could one day overcome expansion. Galaxies would slow their retreat, then halt, then begin to fall back toward one another. The night sky would brighten as galaxies drew closer, stars colliding in bursts of fire, black holes merging in cosmic cataclysms. Eventually, all matter and energy would collapse into a single, dense point, a final implosion that echoes the Big Bang in reverse. Some speculate that such a crunch could be followed by another bang, a new universe reborn from the ashes of the old, continuing an eternal cycle of expansion and collapse. Fire, in this telling, is not an ending, but a doorway. Each scenario arises from the same fundamental question: what governs the fate of expansion? Gravity alone would favor collapse, but dark energy, the mysterious force accelerating the universe, favors expansion without end. The balance of these forces determines whether we face a freeze, a rip, or a crunch. Observations suggest that dark energy dominates, making the big freeze or big rip more likely than the big crunch. Yet even now, we cannot be certain. The future of the cosmos hinges on the nature of dark energy, a riddle we have only begun to probe. Philosophically, these endings are more than physical speculations. They are meditations on impermanence. The Big Freeze speaks of a universe that grows colder and quieter, where time itself stretches into a still eternity. The Big Rip is a universe destroyed not by entropy, but by violence, a tearing apart of the very fabric of being. The Big Crunch offers a more cyclical vision, where endings are beginnings and destruction is creation's twin. Each narrative holds a kind of poetry, a reflection of our own fears and hopes about mortality and renewal. And yet, no matter the ending, there is beauty in the knowing. To understand that the universe carries its fate within it is to glimpse the deep coherence of reality. The same laws that govern the fall of an apple or the flicker of a candle flame also decide the destiny of galaxies and time itself. To ask how the universe ends is to ask how the story of everything unfolds, from first breath to last silence. Perhaps we will never see that ending. The timescales are too vast, the process is too slow or too violent for human eyes to witness, but our questions are not wasted. They allow us to stand at the edge of knowledge and look outward, to imagine futures as strange and grand as the cosmos itself. And in doing so, we remind ourselves that the present moment, fleeting, fragile, luminous, is all the more precious because it exists between the universe's beginning and its inevitable end. The universe will end, but for now, it lives, and so do we. And in that living, between fire and ice, between silence and song, lies the wonder of existence itself. At the deepest edges of knowledge, the language of physics begins to stutter. For more than a century, two great frameworks have carried us. Einstein's general relativity, which describes the smooth geometry of space-time and the motion of planets, stars, and galaxies, and quantum mechanics, which governs the jittery, probabilistic world of atoms and particles. Each is astonishingly successful in its own domain. Relativity predicts the bending of starlight around massive objects, the slow drift of Mercury's orbit, the ripples of gravitational waves. Quantum theory explains the glow of atoms, the behavior of semiconductors, the chemistry of life itself. But when we push both to their extremes, when gravity is crushing and quantum effects roar loudest, the two stories clash. At the very places where answers matter most, the equations break. Black holes are one of these edges. Relativity describes them as warps of space-time so steep that not even light can escape, a singularity hidden behind an event horizon. But quantum mechanics whispers that information cannot simply vanish, that even black holes must obey the rules of conservation. The two frameworks disagree about what happens to matter and energy swallowed into that darkness. Does it disappear forever, as relativity suggests, or is it somehow preserved in a way we do not yet understand? The paradox is not academic. It signals a hole in our understanding, a point where the pillars of physics collapse into contradiction. The earliest instant of the universe is another frontier. Relativity carries us back toward the Big Bang, describing the expansion of space-time to fractions of a second after it began. But when we try to go further, down to the very first moment, the equations blow up into infinities. Quantum mechanics, meanwhile, tells us that energy fluctuates even in empty space, that uncertainty rules at small scales. To describe the birth of the universe, we would need both relativity and quantum mechanics working together. Instead, they resist each other, like mismatched pieces of a puzzle that cannot quite lock into place. Physicists have long sought a bridge between them, a theory of quantum gravity that unites the very large with the very small. String theory, loop quantum gravity, holographic models. These are attempts to knit together the fabric of space-time with the restless granularity of quantum fields. Some are elegant, others wild, all incomplete. Each offers glimpses, hints that the universe might be woven from vibrating strings or quantized loops, that space-time itself may emerge from deeper quantum structures, but no experiment yet confirms these visions. The edge of physics remains shrouded, a mist where mathematics points forward, but observation cannot yet follow. There is a strange beauty in this impasse. Science is often imagined as a relentless march towards certainty, but here we see its truer face, humble, unfinished, aware of its limits. The clash of relativity and quantum mechanics is not a failure but a frontier. It tells us that reality is more subtle than our current maps can capture, that beneath the smoothness of space-time and the flicker of particles lies a deeper order we have not yet uncovered. The paradoxes are not walls, but signposts, pointing us toward what still waits to be discovered. For now, we live in a world straddling both stories. Satellites rely on relativity to correct their clocks, ensuring GPS signals stay accurate. Computers rely on quantum mechanics to control the flow of electrons through silicon. Each framework works perfectly within its domain, even as they contradict each other at the edges. It is as if the universe allows us to glimpse only part of its script at a time, never the whole, keeping the final chapter closed. And so, we circle these mysteries. Black holes that evaporate yet conceal their secrets. The first instant of creation that eludes our equations. The possibility that space-time itself is not fundamental, but emergent, a byproduct of deeper laws. We do not yet know what lies beyond this brink, but the very existence of the brink is an invitation, a reminder that science is not finished, that the cosmos is still larger than our understanding. The edge of physics is not where knowledge ends. It is where wonder begins. Black holes are often described as monsters, devourers of matter and light. But in truth, they are also boundaries, natural endings written into space-time itself. An event horizon is not a surface in the usual sense. It has no texture, no solidity, no wall you can touch. Instead, it is a threshold, the point beyond which all paths curve inward, where every future ends at the singularity. To stand at the edge of such a horizon would be to face a miniature end of the universe, a place where space and time fold against escape. For an outside observer, the horizon is a one-way veil. What falls in vanishes, not by moving faster than light, but by finding that every possible route forward now lies deeper into the black hole. Approaching such a boundary, the experience becomes stranger. Light from behind you struggles to keep pace as space itself curves steeply inward. The stars above seem to distort, stretched by the lensing of gravity. If you tried to resist, no rocket or engine could succeed. Gravity near a black hole is not a force to oppose, but a shape of space-time itself. To fall is not failure, it is inevitability. And then there is spaghettification, a word that sounds almost playful, but hides a terrible fate. As you draw closer, the difference in gravity between your head and your feet grows immense. The nearer part of your body is tugged harder, the farther part less. The result is tidal, stretching so extreme that atoms are pulled apart, matter drawn into long, thin strands of energy. In the final moments before crossing the horizon, your body would be stretched into nothing recognizable. Your fall transformed into a filament of particles, spiraling down into darkness. Yet the black hole does not simply consume. It also conceals a paradox. According to relativity, once information crosses the event horizon, it is gone forever, lost to the singularity. But quantum mechanics insists that information cannot be destroyed, that the quantum state of matter must be preserved in some form. This is the information paradox. Two great frameworks colliding, each correct within its domain, yet incompatible at the edge of a black hole. Some suggest the information is encoded on the horizon itself, like a hologram imprinted in the fabric of space-time. Others imagine subtle radiation carrying it away, scrambled but not erased. For now, the paradox remains unsolved, a signpost pointing to deeper laws we have yet to discover. Hawking radiation adds another twist. Stephen Hawking showed that quantum fluctuations at the horizon can cause black holes to leak energy, faintly glowing as particles escape. Over incomprehensible timescales, even the most massive black holes will evaporate, shrinking until they vanish entirely. What happens then to the information they once held? Is it restored, scattered into the universe as the black hole fades? Or is it forever beyond reach? The question is not trivial. It cuts to the heart of whether the universe itself obeys its own rules. To think of black holes only as destructive is to miss their subtler role. They are laboratories at the edge of physics, where gravity and quantum mechanics clash in their most extreme forms. They force us to confront the limits of knowledge, to admit that our equations, so successful elsewhere, cannot yet tell a consistent story here. Black holes are not simply the end of matter, but the beginning of deeper questions. And yet, they are also strangely beautiful. To orbit one would be to see light bent into impossible arcs, stars circling in distorted halos, time itself stretched into strange rhythms. From a distance, a black hole is serene, a dark sphere ringed by glowing matter spiraling inward, a silence that belies the violence within. At the event horizon, the universe itself seems to pause, as though marking the boundary between the knowable and the unknowable. In a sense, every black hole is a miniature cosmos, complete with its own horizon, its own hidden interior, its own fate. They are ends without edges, voids that swallow not by force but by geometry. They remind us that space itself can curve so steeply that escape is impossible, that endings can be written not in fire or ice but in silence, and in their paradoxes, spaghettification, event horizons, evaporating radiation, they whisper of a deeper physics still waiting to be uncovered, just beyond the boundary of what we now understand. To contemplate a black hole is to stand at the edge of existence, staring into a silence that is absolute. It is to recognize that even within an infinite universe, there are places where the story ends, places where space folds upon itself, where time has no future, where all paths lead inward. And yet in those endings, we find not despair, but wonder, because black holes, more than anything, show us that the universe is not finished revealing its secrets. They are boundaries, yes, but boundaries that point beyond themselves to a truth deeper than the horizon, waiting in the darkness. Imagine, for a moment, that everything you see, feel, and know, the sweep of galaxies, the shimmer of starlight, the weight of your own body, is not what it seems. That the universe itself, in all its depth and detail, might be a kind of projection, its true description written not within the volume of space, but upon a distant boundary. This is the radical suggestion of the holographic principle, that reality, as we experience it, could be an image cast from a surface far removed from us, much as a hologram carries 3 dimensions upon a flat sheet of film. The idea did not emerge from philosophy or poetry, but from the hard edge of black hole physics. Jacob Bekenstein and Stephen Hawking showed that black holes carry entropy, a measure of information, and that this entropy is proportional not to their volume, but to the area of their event horizon. The information content of a black hole seems to be encoded on its surface, not within its depth. If true for black holes, why not for the universe itself? Perhaps the ultimate description of the cosmos lies not in its interior, but on its boundary, a cosmic horizon holding the script from which reality is projected. In a hologram, what appears three-dimensional is in fact recorded as interference patterns on a two-dimensional surface. Viewed correctly, the hidden information unfolds into depth and form. The holographic principle suggests something similar at a cosmic scale, that all the richness of three-dimensional space, perhaps even the flow of time itself, may be emergent, the consequence of information inscribed elsewhere. In this view, the stars above and the ground beneath may be like the flicker of a hologram, real to us, but encoded in ways we cannot directly see. This vision of reality is unsettling because it collapses the distinction between surface and interior, between appearance and essence. If space itself is a projection, then our most basic intuitions about existence are shadows cast from deeper laws. And yet, the principle offers more than metaphysics. It has proven a powerful tool in physics, inspiring connections between quantum mechanics, gravity, and string theory. The mathematics of holography suggests that a universe with gravity can be equivalent to a universe without gravity existing on its boundary, as though two different descriptions whisper the same truth. One of the most striking realizations is that this duality could resolve the paradoxes of black holes. If information is not lost but encoded on the horizon, then the clash between relativity and quantum mechanics softens. The holographic view preserves both, embedding information on the surface from which reality is read. In this way, the holographic principle is not simply speculation, but a bridge, a path toward unifying the great frameworks of physics that otherwise resist reconciliation. To imagine living in a holographic universe is to accept that the boundaries we cannot reach, the cosmic horizon, the edges of black holes, may hold the deepest truths. What we perceive as depth is, in some sense, illusion, or at least emergence. The real story may be etched upon a surface so distant and subtle that we can only glimpse it through mathematics and thought. Yet, even if our lives are projections, they are no less real. A hologram of a tree can still look like a tree. A hologram of a universe can still hold stars and galaxies and the brief warmth of conscious beings. It is tempting to ask whether this makes our world less meaningful, as though being a projection strips away reality. But in truth, it may enrich it. To live in a holographic universe is to live in a cosmos layered with hidden structure, where what we see is both true and incomplete, a reflection of something deeper. It does not diminish wonder to know that the stars are part of a projection. It only enlarges wonder, reminding us that even the most ordinary moment carries within it the strangeness of hidden dimensions and unseen surfaces. The holographic principle remains a conjecture, unproven yet profoundly influential. No experiment has yet confirmed that our universe is a hologram, though hints may linger in the cosmic microwave background or in the fine structure of quantum entanglement. For now, it is a vision, a radical possibility that bends the way we think about space, time, and existence itself. It is a reminder that reality may be far stranger than it appears, and that the cosmos, in its deepest truth, may be written on the very boundaries we cannot see. And so, when you stand beneath the stars and feel their immensity pressing down, you might imagine that their light, their distance, their vastness are part of a pattern inscribed elsewhere, a grand hologram in which we move and breathe. Whether true or not, the principle draws us toward the edges of knowledge, inviting us to look at reality not as a finished picture, but as a projection of something deeper, waiting just beyond the horizon. There is a thought, strange and persistent, that haunts the edges of modern philosophy and science alike. What if the universe is not the deepest level of reality? What if the space we inhabit, the stars we measure, the particles we accelerate, are not fundamental at all, but a kind of program running on machinery beyond our comprehension? This is the simulation hypothesis, and it asks us to take seriously the idea that our cosmos could be, in essence, code, At first, it sounds like science fiction, the premise of a story or a movie, but the reasoning behind it is disturbingly rational. If a civilization somewhere, someday, became capable of running simulations of universes, then the number of simulated worlds could vastly outnumber real ones. And if that is the case, then statistically, the odds of us being inside a simulation rather than outside it are overwhelming. In this view, the question of whether space ends may not be about horizons or geometry at all. It may be about computation. Space may end because the program ends. Think about pixels on a screen. From far enough away, an image looks smooth and continuous. But zoom in, and you see the grid, the smallest units of resolution, the indivisible dots that make up the whole. Some scientists wonder whether the universe itself may be like this, that space and time are not infinitely divisible, but quantized, made of tiny pixels of reality at the Planck scale. If this were true, then what we take for smoothness might in fact be the resolution limit of a cosmic display. The smallest length, the smallest unit of time, may be nothing more than the size of the universe's pixels. In a simulation, boundaries are not like walls but like ends of code. Beyond what is simulated, there is simply nothing, no calculation performed, no data stored. If so, then perhaps what we call horizons, the cosmic limit of what we can observe, are not just features of physics, but artifacts of design, the edges of what has been rendered. Could the observable universe be a kind of window into a program running elsewhere, the visible portion of a far larger but selectively computed reality? The hypothesis does not answer, it only deepens the question. If this idea unsettles us, it may be because it collapses the distinction between real and virtual, natural and artificial. We are used to thinking of reality as solid, grounded, beyond question. But if reality is code, then even solidity is illusion, just a set of instructions producing behavior. The warmth of the sun, the pull of gravity, the flow of time itself. These would all be outputs, results of deeper rules running on a substrate we cannot see. The programmer's hardware is, by definition, outside our universe. We could never touch it, never measure it, never know it directly. And yet, if we are simulated, we are no less real to ourselves. Pain still hurts, joy still uplifts, love still binds, death still wounds. The fact that a world is simulated does not strip away the experience of living within it. A hologram still dazzles the eye, though it is only interference patterns. A dream still feels profound, though it vanishes at waking. Reality, in this view, is defined not by its fundament, but by the coherence of its laws, by the way it sustains experience. Whether code or cosmos, what matters is that it holds together, that it gives rise to beings capable of asking these very questions. There are those who believe we might one day detect signs of simulation, little glitches in the code, evidence of resolution limits, or computational shortcuts. Perhaps the cosmic microwave background holds repeating patterns, hints of compression. Perhaps high-energy physics will reveal that space is grainy, not smooth. Or perhaps the clues will always remain hidden, the program written so elegantly that no test within the system can reveal what lies beyond it. If we live in a simulation, it may be flawless. Still, the idea lingers. If reality is computation, then space could end not at a horizon of light, but at the end of code. The outside of the universe would not be emptiness, but something unimaginable, like the circuitry of another realm. And the question of whether space ends becomes less about geometry and more about design. The simulation hypothesis is not universally accepted. Many dismiss it as philosophy disguised as physics. But even as speculation, it exerts a powerful pull. It forces us to reconsider what we mean by real, what we mean by true. It reminds us that even our deepest assumptions, that space stretches without question, that time flows unbroken, might be artifacts of a larger structure. Perhaps we are simulated, Perhaps we are not. But either way, we live, we think, we wonder, and in the end, that wondering itself may be the most remarkable thing. Evidence that whatever reality is made of, code or cosmos, it has given rise to beings who look at the stars and ask whether they are written into the program of existence or shining in a universe all their own. When we look up at the night sky and try to imagine infinity, something in our minds falters. We can picture great distances, far-off stars, clusters of galaxies. We can even attach numbers to them, multiplying zeros until the scale becomes absurd. But infinity is not a number. It is not a distance we can traverse or a quantity we can count. It is something without end, without boundary, without completion. And our brains, evolved to throw spears and gather fruit, strain against its immensity. We live in bodies that measure the world through limits. Eyes perceive only a sliver of the electromagnetic spectrum, ears only a thin band of vibrations, skin only a narrow range of temperatures before it burns or numbs. Our minds extend those senses with instruments, building telescopes to catch invisible light, detectors to measure elusive particles, accelerators to probe the smallest scales. Yet even as our tools expand perception, our brains must translate the data into concepts we can hold. And there is the problem. The universe is not obliged to fit within the shapes our minds evolved to grasp. Infinity, in particular, resists us. We imagine lines stretching forever, but in doing so, we picture something finite, simply extended, a road without end. What we do not truly grasp is that infinity is not lengthened finitude. It is different in kind. We imagine time unrolling endlessly, but still we hold in our heads a film strip, frame after frame, always countable. We cannot picture infinity because we are creatures of edges, always seeking closure, always craving borders to make sense of scale. Cognitive science shows how deeply this is wired. We learn numbers as children, and while we can grasp bigger without end, our minds always anchor to reference points. 1,000 is larger than 100, 1,000,000 is larger still. But once we move into the billions, trillions, quadrillions, the numbers lose shape. We nod at their immensity but feel no real difference between one unimaginable figure and the next. Our brains collapse infinity into a vague blur of a lot, unable to hold the true idea of endlessness. The same is true for the very small. The Planck length, the shortest possible unit of space according to physics, is 20 orders of magnitude smaller than an atom. To the mind, this is no different from saying too small to see. Both collapse into the same category, beyond us, in both directions, vastness and minuteness. Our perception crashes against cognitive walls, and so, when scientists describe space as possibly infinite, or time as stretching forever, we translate those concepts into metaphors. We picture loops, sheets, balloons, saddles, branching trees of universes. These analogies help us approach the truth, but they are never the truth itself. They are scaffolds built to hold what our minds cannot directly bear. When we ask if space ends, we are as much confronting the edges of thought as the edges of physics. There is something humbling in this recognition. The limits of perception are not just biological, but conceptual. Just as eyes cannot see beyond visible light without instruments, so minds cannot think beyond certain structures without metaphor. We are bound not only by the physics of the cosmos, but by the architecture of our cognition. The universe may be infinite, but our ability to imagine it is not. And yet, those limits do not diminish us. They give rise to wonder. To stand before infinity, to feel the brain strain and fail, is to experience awe in its purest form. Infinity is not meant to be held. It is meant to remind us that we are finite. Our comprehension has edges, and those edges are as real as any cosmic horizon. The fact that we cannot fully grasp infinity does not lessen its existence. It only deepens its mystery. So, when we think about the end of space, We are wrestling not just with astrophysics, but with ourselves. We are confronting the fact that our questions stretch farther than our perception, farther even than our cognition. Beyond the physical horizon lies a cognitive one, a place where imagination stumbles, where thought itself meets its boundary. That, too, is a kind of ending. And maybe that is the truest definition of infinity. Not a number, not a size, not even a destination, but a mirror reflecting the limits of human thought. To glimpse it is to recognize that we will never contain it, that it will always remain outside us, vast and ungraspable. But in the attempt, in the reaching, we discover the grandeur of being human, small, finite, yet able to look into the abyss of forever and name it, even if we cannot hold it. Long before telescopes and equations, human beings looked to the skies and asked where it all began and where it all might end. The answers they offered were not measured in light years or particle fields, but in images, symbols, and stories. The cosmos was not an abstract expanse of matter and energy. It was a living structure, a sacred order, often fragile, sometimes eternal, always imbued with meaning. To imagine its edges was to imagine the limits of existence itself, the place where human life touched mystery. Many ancient cultures spoke of the world as emerging from a cosmic egg, a single whole shell containing both beginning and boundary. In Hindu traditions, the golden egg, Hiranyagarbha, floated upon the primordial waters, splitting open to release the universe. In Orphic Greek myth, the egg was encircled by a serpent, cracked by the force of creation, and from it emerged the first gods. The image of the egg carried a paradox. It was finite, a shell enclosing all things, but within it lay the infinite potential of existence. To live in a cosmic egg was to live inside a container both nurturing and absolute. Beyond the shell, there was nothing. The end of space was not void, but the smooth curve of a cosmic womb. Other traditions imagined the world supported by great creatures. In Chinese mythology, the giant Pangu split the chaos and grew until his body itself became the world. His breath, the wind, his blood, the rivers, his bones, the mountains. In many indigenous stories across North America, the earth rests upon the back of a colossal turtle, swimming through cosmic waters. This vision is not one of abstraction, but of grounding. The universe ends not in equations, but in the strength of a living being who carries it. The turtle's shell is both floor and boundary, a dome above which the stars shine, below which lies the deep. Here, the end of space is not. Frightening but stable, steady, sustained by life itself. Domes and vaults, too, recur across cultures. To the Mesopotamians, the sky was a solid firmament, a great dome of lapis lazuli stretched above the flat earth, holding back the waters of chaos. In the Hebrew Bible, the firmament separates the waters above from the waters below, a boundary hammered out by divine hands. To the Norse, the skull of the giant Ymir was stretched into a dome to form the sky, its edges resting on the earth's horizons. In each case, the heavens were not infinite, they were a roof. To look upward was to look at the inside of a structure, a ceiling whose edge was both protection and limit. Beyond it lay mystery, chaos, or divine presence. Even in cultures that imagined cycles rather than boundaries, the cosmos carried edges of time, if not of space. In Hindu cosmology, universes are born and destroyed in endless cycles, each lasting billions of years, breathing in and out like the rhythm of a cosmic being. In Mayan tradition, worlds are created and destroyed in succession, each one with its own order and its own end. Here, the cosmos does not stretch into infinity, but loops through beginnings and endings. The edge is temporal, not spatial, a reminder that worlds can collapse and begin anew. What unites these visions is the human need to frame the infinite in images we can hold. An egg, a turtle, a dome, a cycle. Each is a metaphor for the unimaginable, They transform the unfathomable vastness into something domestic, something that echoes human experience. Eggs hatch, turtles carry, domes shelter, cycles repeat. In this way, ancient cosmologies gave people not only an account of the cosmos, but also a sense of belonging within it. The end of space was not a cold abstraction. It was a story, and humans had a place in that story. Even today, echoes of these ancient ideas linger in our language and imagination. We speak of the universe expanding like a balloon, or of space-time as a fabric stretched thin. We imagine multiverses as bubbles colliding, worlds stacked upon worlds. Our metaphors have shifted, but the impulse is the same: to take what cannot be pictured and wrap it in images drawn from daily life. We are still telling stories to make sense of the edges, still reaching for symbols to hold what the mind cannot fully grasp. Perhaps this is the deeper lesson of cultural and philosophical edges. The universe may or may not have a boundary, but our thought does. To face infinity directly is overwhelming. To face it through myth is to render it intimate. Ancient cosmologies remind us that the end of space, however conceived, is also the edge of imagination, a place where science and story meet. We may now speak of horizons, inflation, and dark energy, but beneath those terms lives the same human urge that once saw a turtle's back, a dome of stone, a cosmic egg floating in the void. In every age, we look outward and wonder, where does it all end? And in every age, the answer reflects not only the cosmos, but ourselves. There is a kind of solace in admitting that we do not know. For all the instruments built, the equations written, the models tested, the question of whether space ends still hovers beyond our reach. We can draw horizons, measure redshifts, imagine inflations and multiverses, but the final truth remains veiled, and maybe it always will. The human mind, brilliant and restless, seeks completion. Yet the cosmos reminds us, gently but firmly, that not everything is ours to hold. Mystery has its own kind of gravity. It pulls us toward reflection, drawing our attention away from certainty and into wonder. There is peace in letting the infinite remain infinite, in recognizing that the very act of not knowing is itself part of the beauty. If we could pin down the universe in a single answer, wrap it up neatly with equations and diagrams, would it not lose something essential? It is the open-endedness that keeps us leaning forward, keeps our eyes on the sky, keeps us building stories and tools and dreams to bridge the gap between us and the unreachable. The comfort lies not in ignorance, but in relationship. Mystery is not a wall keeping us out, but a horizon inviting us on. The stars do not give away their final secret, but they give us their light, and in that light we find enough to wonder, enough to live. To rest in the unknown is to remember that knowledge is not the only measure of meaning. Awe, humility, curiosity, these too sustain us. So we circle back to the central question: does space end? Perhaps, perhaps not. Perhaps the question itself dissolves when carried far enough. But whether infinite or bounded, expanding or looping, hologram or simulation, the universe is what it is, a vastness in which we find ourselves briefly awake, able to ask, able to marvel. There is no urgency to the answer. The stars will go on shining, the galaxies will go on drifting, the horizons will remain where they are. Our place is not to solve it all, but to stand in the middle of it, breathing, listening, feeling small, and yet somehow deeply connected to everything that exists. The beauty of the infinite is that it will always exceed us. And the beauty of being human is that we can find peace in that, drifting not into despair, but into wonder, letting the unanswered carry us gently into stillness, like waves fading into the quiet of night.